And I'll say welcome back, everybody, to PCB Design Fundamentals Part 2. We'll pick up where we left off on Monday's class. I believe we had just finished up the discussion about final inspection right here, where I was pointing out the fact that even though we have all of this wonderful automated inspection capabilities, the automated optical inspection, and so on, that it's still incumbent on us to also make sure that we're doing proper bring up in functional testing, as AOI can miss some defects, especially mechanical defects like I shown here with this damaged capacitor that was, because of the way it was soldered in, was not obvious from an optical point of view. Continuing on with manufacturing. Now, some of the stuff in the next few slides here is targeted at specific market segments, high reliability, and so on, or if you're in a broader temperature range and so on. Really targeted more at my mil aero students and my mil aero class. So if you come back for mil aero, you'll see some of this again, but we'll go through a couple of points here regardless. So if we need high reliability and long product life, uh, or other extreme environments, we have a different set of considerations we need to take into account than if we're doing simple consumer goods. As my example here, if a cell phone dies, it's no big deal. You go to the store, you get a new one, right? You go to T-Mobile or AT&T if you're here in the States, or whoever your cell phone carriers, and say, hey, my phone died, and you get a new one. On the other hand, if you're building like a higher reliability product or a more extreme product, such as like deep sea ROVs, like the remote operated deep sea subs, if that dies at the bottom of the ocean, often difficult and costly to repair or even get a new one. Not only is the unit expensive, if it's down at the bottom of the ocean, sending another deep sea ROV to pick up the first ROV, might be a problem, etc. Additionally, it's often recommended in high reliability applications to use the low density level footprint. So if you remember back to course 1, where we were actually creating our footprints, and I talked about the 3 different footprint density levels, the A, B, and C, that the level A or MMC footprint design allows for the most robust solder joint, but due to requirements of increased complexity and reduction of envelope in modern designs, you can't always fit a level A density. Most designs I've done in my career have been level B density designs. Good trade-off between robustness of a solder joint without taking up too much of my board space, and so on. In addition to regular Class 3 fabrication requirements, for assembly, which we'll talk to here shortly, the J Standard 001, there is actually, for products going into outer space, there's a space addendum to J Standard 001 with even stricter assembly requirements for the printed board assembly. Not all extreme environment applications require the use of this addendum, and additionally, any of the addendums, whether it's the space addendum, the automotive addendum, the medical addendum. So IPC has produced several different addendums for specific market segments, specifically military aerospace, um, space addendum to mil aero, the automotive market segment, the medical market segment, and so on, where there's often very special considerations in the fabrication or assembly processes. If you are referring to an addendum, the addendums are not required to be adopted in whole, right? You can selectively or partially set your requirements to these addendums. You can say, I want my board assembled to J Standard 001, with the exception of, say, gold removal on terminals. I want that to the space addendum of J Standard 001, or whatever the case is. The majority of space addendum contains scope modifiers, and that's why I'm going to use the gold modifier here as an example. So the majority of the addendums, in this case I'm talking the space addendum, but the automotive and the medical addendums are the same way. They are typically scope modifiers to the existing clauses in the J Standard 001. And they simply usually change the pass-fail criteria or the magnitude of the requirement. As an example, in the base J Standard 001, section 4.5.1, requires 95% gold removal only from surfaces with greater than 100 micron of gold thickness. Think like gold-plated terminals, like, if you've got like a connector or something and you go for the gold finish instead of the tin lead or matte tin finish on your terminal. So if the gold flash on those terminals, the solder terminals, is 100 microns or thicker, J Standard 001 base standard says you must remove 95% of that gold before you solder to mitigate gold embrittlement. On the other hand, the space addendum to JSTOWN 001 requires the 95% gold removal from all surfaces, regardless of the thickness of the gold. See, it's a same clause, slight modification to the requirements of the clause. Okay. Additionally, qualification. All boards go through some level of qualification. You as designers will choose what that is. For high reliability designs, often you have extended qualification testing of the design prior to production fabrication. When we say qualification, what we're basically talking about is testing, right? The prototype testing level, and at what point is the product or the design deemed acceptable to go to production, right? Now, for a consumer good, it might be I built a prototype, I tested it, it appears to function, go to production. On the other hand, if I'm building, a NASA rocket ship to go to the space station, or better yet, the Art Ares program, I think it's Ares or Artemis. I think Artemis is going to the moon and Ares is going to Mars, are the two big program names at NASA right now. But if I'm working on either of those programs, I better test that product, 8 ways to Sunday and then some to make sure it works under all possible conditions and there's no way I have a product system failure once I'm out in space or heading to Mars or something like that. So in that case, you may require more extensive testing and qualification, often require building test samples of the PCB and the assembly and subjecting them to tests and validations that are outside the tests that are specified in 6012 and JSTOWN 001. I'll show you what those are here shortly. Often these tests may be destructive or they could still be non-destructive. And you need to document and specify on the master drawing and procurement documentation what any special testing or qualification requirements are. And sometimes these tests require oversight from an authorized design authority or design authority individual. In the case of military, oftentimes when you are performing the qualification testing of your product, it's not enough that you, the company, are performing that test, but they require an official from the government or the military to be present to witness the performance of the test in order to sign off that the test was completed and is acceptable. Tailored test and certification. So in addition to completely custom testing, some designs can use tailored testing of the standard test defined in 6012 and 001. Usually involves following the defined procedure but changing test parameter, magnitude, or duration. For example, thermal testing, right? Where the J standard 001 or the 6012 might require that you thermal cycle the board 5 times before you say that yes, it passes the whatever the test criteria is. You might say, I want you to follow that procedure, but I want you to cycle the board 50 times instead of 5, or things of that nature. Or you might say, cycle it 5 times, but instead of only going to 110% of operating temperature, go to 150% or 200%. Things of that nature. So you can do these tailored testing. Special certification is often required in these applications as well, where a standard test may require only a COC or a certificate of conformance, which is basically a statement from the testing location, either the fabricator, assembler, or third-party test out that just says, yes, I passed the specified test. So basically a pass-fail certificate. Whereas if you're doing a tailored version, you might require full test data results to be provided along with the COC so that you can have independent data analysis if you want, and so on. So again, all of this would be documented on your master drawing and your procurement documentation. Other examples of tailored testing and qualification may include bake out all boards regardless of age, increase thermal stress testing temperature, increase the stress testing number of cycles. I already mentioned those two. Adding vibration testing, adding shock testing, increasing the voltage breakdown or high pot testing voltage levels. Just to name a few. There's many others out there, whatever you deem necessary for your product. In almost all modern board designs, especially those as we do more and more printed and wearable, outdoor rated product design, we're going to need the use of a conformal coating. I've mentioned conformal coatings before, but we'll talk about them a little bit here. There are some special considerations taken into account when dealing with conformal coating. CTE mismatch is going to be more critical in your design if you not only have the printed board material below your compounds, but now a encapsulant material, such as conformal coating, above your product. Again, all of these have some stiffness or some resistance to movement or expansion contraction rates that vary from the expansion contraction rates of the board and the product. And so you can effectively have one part of the material moving into the other part of the material, basically pushing against a solid wall, kind of things. Thickness of conformal coating after curing is going to be more critical, often if you've got a reduced envelope. So not just the high reliability like military aerospace, but think like smartwatches, fitness trackers, cell phones, and all these kind of products where you might have, you don't have a lot of volume inside the housing in order to allow for, overly thick coatings of materials. And if you're doing space applications or anything with a low pressure environment, uh, outgassing effects are going to be important. In low pressure, high vacuum environments, gases trapped in solid materials, especially things like coatings, can escape into the surrounding environment. These free gases can then settle and condense on solid surfaces. If these surfaces are critical, such as optics, sensors, etc., they can be rendered inoperative due to the presence of this material. Also, if it's a man-rated vehicle, think Crew Dragon or New Shepard, SpaceX and Blue Origin's, modules that take humans to space. Think Orion from NASA, the old space shuttle, the Soyuz capsule from Russia, and so on. Anything where humans need to exist in a low pressure, high vacuum like space environment. Any entrapped gases that get released into that environment create a toxic environment to the humans, and so on. So we need to consider those. Also, since conformal coatings are applied as one of the last or final steps in the assembly process of a product, they have a higher likelihood of having outgassing issues, right? Uh, Materials that are applied early in the process will naturally outgas as the product keeps going through the processing steps, and so you might not have as much of a problem. NASA and other standards organizations do have standards and requirements and specifications to define the allowable amount of outgassing for different materials, as well as a list of prohibited materials. Again, that's all typically here on Earth. If you're doing standard products, consumer goods, industrial goods, whatever you're working on, unless you're going into outer space, you typically don't have to worry about outgassing effects and so on. The application of conformal coating should follow the requirements of IPC J Standard 001. Due to corona effects, I say described previously, I borrowed the slide from my military class. This class has not talked about corona effects. So we'll ignore that for now. But due to corona effects, it's critical to not allow any trapped environments under device bodies. For this reason, it's recommended to use a low viscosity conformal coat that can flow under the compounds, with brush-on and dip coatings being problematic, and try to avoid these, including silicons and some of the epoxies are some of the thicker, more viscous ones. Again, it also depends on the formulation, right? You have to look up the data sheets and material information, talk to the vendors or distributors of the conformal coats, and let them know the types of parts you have. They will often have recommendations of slightly different formulations, lower viscosity, higher viscosity, and so on. In the event that even a low viscosity conformal coat will not fill under the part bodies, the use of an underfill or underfilm may be necessary. These are special materials that are injected or placed under the body of the part during or right after solder to ensure a complete environmental seal after conformal coat application. And I should say, or uh, they ensure a complete environmental seal and or a mechanical support, and we'll see what I mean here in the next slide here. Okay. So underfills, they're formed in a liquid, they're in a dispenser, and they're of a low enough viscosity that using capillary action, think like BGAs and parts like that, where the material through capillary action will fill the area under the BGA that normally would not have gotten encapsulated with a standard conformal coat. Standard conformal coat would have curtain coated on, just kind of formed a fillet here, but you would have still had that micro environment trapped here. If it's critical that you have no micro trapped environment, again, space or low low pressure, high vacuum environments, or other environments where you need to ensure that full encapsulation under the body, then an underfilm can work. It's applied as a liquid and dispensed. Often they can be only at the corner if you need them only for structural or mechanical needs. So in this case, we're using it similar to a staking compound right here, allowing it to flow under, but only at the corner of the device right here. Or it can be used like we have on these, looks like memory chips right here, where we needed to fill completely underneath the part, and therefore we did a complete 360-degree perimeter and allowed it to completely fill under with the capillary action. Usually most of these materials have some form of color change dye added to them. So when they're first applied, they're a blue color, and then after they've reached full cure, the dye changes color either to a clear or a gray, as you see right here, indicating that the material has fully cured. The other form they can come in is under film, similar to the prepreg materials we talked about last week, where it is a partially cured resin that can still go through a phase transition back into its liquid state or viscous gel-like state for prepreg. In this case, a liquid state for these, but it's supplied or provided in a solid state in these little strips or whatever shape you need. The nice thing with the under film is it can be supplied on tape and reel, so it can be placed with the same pick and place machine that places the parts, and you'll see it can be placed right here along the edges. And the heat of the soldering process, as soon as, and the timing is configured to where first the soldering occurs, and then that heat causes the under film sheet to liquefy and then flow under and around those parts as well. And again, you get the same kind of clear translucent sealant there completely underneath the body of like BGAs, QFNs, DFNs, and the like. Okay, so still uses capillary action, but placed as a sheet of material during component placement, and the heat of the soldering process changes the material into the low viscosity liquid that flows under the body. One particular type of conformal coat that can help ensure complete coverage and low impact to volume and envelope is Parylene. Parylene is a gaseous polymer that is applied in a vacuum deposition process. Requires specialized equipment to apply, with very few shops apply Parylene in-house. And when I say shops, I mean fab shops. Most of your fabricators have in-house capability, or I'm sorry, not fabricators, assemblers, because this is after component assembly. Most of your assemblers have like spray booths that can apply acrylic or epoxy or urethane. They have the dispensing means to inject the capillary action of the underfills and so on, but very few assembly shops keep a Parylene coating system in-house, and we'll see why in the next slide right here. Requires specialized equipment. Very few shops have Parylene, usually sent to specialty shops for Parylene coating, which will require extra level of vendor certification oversight and usually adds extra time or cost to your product. Due to the gaseous vapor deposition process, special care is needed and necessary to protect or prevent unwanted surfaces from being coated. Unwanted surfaces, think things like connector pins, test points, and so on, right? So connector, right? Right. So think things like connector pins, test points, etc. Anything where you want to have access to that metallized surface after the application of the conformal coating uh, needs very special care. Since this is a polymerization process and not a standard cure process, once applied to a surface, the only way to remove it is by mechanical abrasion, typically micro glass bead sandblasting, making rework extremely difficult with these compared to uh, other products like epoxies, urethane, silicones, where simple chemical solvents can usually strip the conformal coating off of the board. In this case, we're now going into abrasive sandblasting to remove the material. It also easily gets on pins and sockets of connectors through shells that would prevent traditional conformal coats. So again, think if you have like a through-hole connector soldered into your board, I can usually just put a piece of masking tape around that connector, and due to the higher viscosity liquid nature of a traditional conformal coat, it will simply get to the masking tape and won't flow inside the shell of the connector. On the other hand, because we are now in a gaseous state and pulling a vacuum, the slightest little pinhole, micro crack seal where the two halves of a back shell come together, anything like that, is an ingress path for this gaseous vapor to get on the pin, so it makes it very difficult. In fact, most of the time when I've done paralleling, what I've basically done is said any parts that I need to have a knot coat with the paralleling, I actually don't even solder in until after the paralleling coating, and I completely at the surface do a coating protection over the solder pads. So rather than trying to protect a three-dimensional structure, I'm protecting a two-dimensional surface on the board. Just like with other materials, like the underfill we talked about, or other conformal coats, the material for the paralleling can be clear or it can be colored to make for an opaque coating for optical security of products. So describing paralleling here really quick. Again, with a traditional conformal coat, epoxies, urethanes, etc., you curtain coat or spray that material on, but because of the viscous nature of it, you get this kind of uh, um, fluid dynamics here where you get this kind of doming effect right here, but they often do not flow underneath the body of parts or between very close parts. Or if I have a wire coming off the top coming down to the board, that won't necessarily get coated here the way it will. There's paralleling, on the other hand, due to the gaseous vapor deposition process, it uniformly and evenly coats every single surface, including under component bodies, these little corners where air can get entrapped, between the part bodies here, and even these exposed wires. So how does the paralleling work? The paralleling starts as a dimer, and for those, just as a refresher from chemistry class, a dimer is a molecular chain made up of two molecules of the material. A monomer is a single molecule of whatever the material is, and a polymer is a long chain, multiple molecule chain, at least three, typically longer chain of the material here. So we start with whatever our base material is that's going to become our paralleling in a dimer form. We then go through a vaporization or sublimation process. So we go from solid directly into gaseous state without going through liquid, kind of like the when you put dry ice, it starts going directly into gas without going into the liquid state. Once it's in the gaseous state, it's still a dimer. We then go through pyrolysis, and this is the problematic step right here. Pyrolysis is extremely high temperature to break the dimer into a monomer. We're talking temperatures of the 650 to 690 degrees C range, far above the decomposition temperature of our board. But that's okay, our board is not in here. This is simply processing the chemical material of the paralleling itself. The board itself is contained down here in the deposition chamber, which is kept at a cool room temperature, 30 to 50. It's kept at room temperature, and it pulls a vacuum between 30 to 50 millitorr of pressure. So near hard vacuum is pulled in this chamber. This contains your board as the monomer is injected into the chamber, and by pulling the vacuum, the monomer will settle uniformly uh, onto the surface, creating the polymerization. So unlike all the other conformal coats, which still use adhesive bonding that we talked about on Monday, now we're actually talking polymerization. This is an actual chemical process as opposed to an adhesive process, which is why once applied, the paralleling is very difficult to remove, very difficult to rework. You have to use an abrasive sandblasting to remove that. And again, it does require large specialized equipment with these high temperature pyrolysis ovens in order to form this process, which is why most assemblers do not like to keep these in-house. Just like conformal coatings, potting compounds are our next material we're going to talk about or process. Potting compounds are applied at the end of the assembly process during the box buildup. Potting compounds are used to create a pressure-tight enclosure, provide structural support to the enclosure, and secure the assembly into an enclosure when mounting hardware is not an option. As with conformal coating, CTE mismatch and outgassing are concerns with potting compounds. Potting compounds, however, typically employ some form of material expansion during the curing and setting process. which is necessary to ensure that all cavities and crevices are filled. Again, think like if you've ever done any on your homes or uh, driveways or anything like that, the repair foam that you inject into like a crack or a crevice, and it starts to expand to fill the crack or crevice. They tell you not to overfill it because it'll put too much pressure behind the wall or could actually come back out. Same idea here. Uh, Typically, most potting compounds, unlike conformal coats, will typically employ some amount of expansion to ensure that they properly fill the cavity. This will also add this expansion, will add mechanical stresses on parts and boards if you overexpand. We need to ensure that the expansion rate is considered when filling the cavity, as too much fill can overexpand and damage the board or the assemblies. Additionally, it is often necessary to provide an access hole in the enclosure wall to inject the potting compound. So again, if I'm trying to fill a sealed housing, I might have to have, the entire board put in the housing, the lid already covered on there, and just have a little access port. But if I'm going through the access port method, then we need to ensure that there's an air escape path, because if I just have the access hole, put my needle tip in there, and the needle tip is near tight seal to that, I might not have enough air escape path, and then I try to put the potting compound in there, but an air bubble forms underneath it, and I don't get a proper fill. This injection or escape hole can be a shielding discontinuity if it's not covered back over. Again, if you're concerned with shielding necessary for either EMI or radiation, if you're working in a radiation environment, and not all radiation environments are military. There are medical radiation environments as well. Think X-rays. Think I don't believe CT scan uses radiation, but there are some other radiation treatments, uh, like the radiation treatments for cancer patients and so on. Any of those radiation sources, the machinery that controls those radiation sources, are susceptible to radiation environments. And so extra steps for shielding need to be taken into account. The use of a cover plate with an EMI gasket for EMI levels could be used, or a cover plate of sufficient material and thickness for radiation levels may be necessary. As with other materials discussed, the final material we're going to look at, yes, I see a hand. I don't know if that's a clapping hand from Edson or if that's a question hand from Edson.
As just one point uh, related to coating,
Hmm.
for project related to RF, it's necessary some problem related to the electrical material. If
Hmm.
you use the some protector PCB like silicone or coating, you can alter the dielectric
Yeah.
of the
So,
surface. So
yeah.
need to be careful.
Yeah. Great point, Edson. I actually cover that. I have a whole class on RF design where I go into that. I don't normally talk about that in this class. This is a fundamentals class. But great point, Edson. Thank
Yes,
you for the
yes.
comment.
Just to you explain much better than me. Just to be
Mhm.
careful to if you have a project with
Yep.
RF.
Yep. Like I said, I've got an entire class on that in the RF. So if you're interested, um, uh, I'll be happy to go over that with you. But yes, as Edson says, uh, all coating materials are, all materials have a dielectric. So if you have any dielectric concerns, uh, then take that into account when you are applying your materials to the boards. As Edson said, if you happen to have RF structures on your board, such as antennas for like Wi-Fi or Bluetooth that happen to be running in the RF spectrum, you may need to mask and keep those areas clear of the conformal coating so that you do not alter or affect the behavior of your antenna structure or your RF structures. But again, if you're interested in RF design, RF board design, please come back after the first of the year when the new round of classes starts, and I have my RF class starting again. Okay, as with other materials discussed, staking materials must also be carefully selected. Due to the more rigid nature of staking materials, CTE mismatch and mechanical stresses are particularly important. Outgassing is also problematic with staking compounds, with the rigid nature of the material tends to trap more gases than the more malleable conformal or potting compounds. Destructive analysis is usually necessary to ensure staking material meets requirements, and these may include adhesive or retention strength, actually peeling the part or pulling the part until it actually fails to understand what the peel strength is, vibration and shock testing to make sure it'll stay secure to the board, thermal testing to make sure you won't have any stress fractures and or damage to your staking materials, and so on. Again, I cover more that stuff in more detail in my mill aero class and extreme environments class than I do here in in this class. Due to the complex design of most extreme environment designs, the extreme environment design. Due to the complex design nature of most of these designs, it's often necessary to design special manufacturing aids. Again, if you require special manufacturing aids, standard boards usually don't require those, depending on the shape and structure of your board. But those might include fixtures to align through-hole pads to heat sinks, a stiffener to maintain board coplanarity to support large, heavy parts. Now, that's something you will see even in standard designs, especially if you're doing consumer goods, where we still have transformers for where we're bringing in the 120 volts from the wall and we need to go through a transformer to convert the AC to DC, as well as step it down into the lower voltage that the rest of the system is going to use, and so on. So you might see a fairly large, heavy transformer part mounted on the board in one spot. And oftentimes you need a stiffener to support that while you're going through the assembly equipment before you get it mounted into your actual product. Alignment pins for anti-rotation, features designed into the board break-off rails, connector alignment, rings or tools, or anything like that. Anytime you're doing a custom manufacturing aid, this is where you, the design organization, are designing this manufacturing aid, not necessarily where you're relying on your assembly house to come up with those aids. But if you, the design company, the design organization say, the only way we're going to get this to properly align into our housing after the board comes back from assembly is to use some special alignment tool to make sure all of our connectors are properly soldered into the solder pins with exactly on center and not clocked or rotated or cockeyed a little bit. So if you're designing the custom assembly aids, then it's important that you make sure that that aid is completely designed, finished, and tested and verified before you go spend money to get your board assembled. This actually happened to me at one company I was at, where the mechanical engineer was supposed to be designing a mechanical fixture. The board was designed. I was told to send the board out for prototype fabrication, and the mechanical designer had made a mistake and did not verify with me. And so they went off and got the manufacturing aid fabricated, and the manufacturing aid never worked, and we had to redesign something. So it's always a good idea when you're designing manufacturing aids to make sure that you've completed both the design of the board and the manufacturing aid before you go off and have either one actually fabricated. Okay. Again, so some of those alignment tool ideas could be, if you need a special bar to hold all of these uh, parts here relative to the heat sink here, right? Because when you're going through the assembly, the soldering process, this heat sink is obviously not there because there's no way I'm going through a solder machine with a huge extruded aluminum heatsink already mounted to my board. I'll never get the parts hot enough, right? Or this one here, I have a through-hole transistor, old TO220 transistor body right here. And I need to make sure that not only is it placed in the holes correctly here, but it's the correct z-axis height off the surface to align for the heatsink here. So again, some kind of fixture or tool to hold this at the correct z-axis height off the surface of the board. Final topic we're going to talk about here is etchback from a manufacturing process. Not to be confused with undercutting that we talked about on Monday's class, the natural behavior of the acids to cause that trapezoidal shape. But etchback was developed, originally believed it would form a more robust intermetallic connection at the conductive layer to plated through hole wall interface. Again, during the plated through hole formation, where first we do the electrolysis, then the electroplating process that we looked at previously, we show just the face of the layer, right? When we drilled through, we showed just a single face, vertical face would be the connection point. In traditional plated through hole design, the barrel wall is attached to the exposed face of the conductive layer, and this can lead to a shearing force during any expansion contraction from temperature changes. Due to wide operating temperature of some designs, the amount of shearing force can cause a cracking or separation of the conductive layer copper from the plated through hole barrel. The use of etchback is going to change this force from a shearing force to a bending force. Additionally, it is believed that etchback provides more surfaces for the copper plating to adhere to and therefore is believed to be a stronger copper connection. I say believed. This came out of, I believe, the U.S. Department of Defense military from historical designs where this was actually a true statement. As the fabrication and manufacturing processes have evolved and improved over the decades, the strength of the copper plating to the barrel wall is now strong enough that it's equivalent to what we have from the etchback. But if you still are in a wide temperature environment, the use of etchback will still change from a shearing to a bending force. And I'll show you what I mean right here. In a traditional plated through hole, the exposed copper of the layer right here is planar, z-axisly planar here with the barrel wall right here. And so during the plating process, I have this single plating surface right here at this face. And during the z-axis expansion of the barrel wall, all of that force is applied right here at that vertical line interface, causing this to become a shearing force. I am literally putting my force trying to shear that intermetallic bond that was formed during the plating process right here. Okay? Etchback, on the other hand, is going to change that to a bending. Now, there are actually two types of etchback: positive or traditional etchback, and then what we call negative etchback. We'll get to negative etchback in a minute here. But traditional etchback removes some of the glass or resin around the copper of the exposed layer, exposed face of the conductive layer, and this is referred to positive etchback or just etchback. If you say, I want etchback on my design, you'll get positive etchback here. The removal of the materials between 5 micron and 80 micron with a preferred removal of about 13 microns. The removal process involves a combination of chemical solvent-based and mechanical scrubbing-based methods. And due to the nature of the solvents used in the etchback process, a residue of resin and other contaminants is often left on the surface that now must be removed before plating, right? Okay, I've made this protuberance of copper, which we'll see here in a moment, but if that, exposed copper now has a residue of resin and glass and solvents and other things, well, the plating's not going to stick to that very well or plate to that very well. So now I have to go through a second process to now clean the copper surface. The second, the second removal is referred to as smear removal and is done to ensure a clean and viable surface for the plating process. Smear removal is a maximum of 20 microns, and the total combination of material removal from etchback, smear removal, drilling, etc. shall not exceed what is listed in Table 3-10 of the IPC 6012, which we'll look at here shortly, okay, for rigid boards. Now, what do we mean by positive etchback? So what we're talking about here is we're going to look at, here's the copper of my layer. That's what one is. That's my internal conductors. Here's my glass and resin, and I'm going to use chemical solvents and scrubbing methods to literally eat some of that away. So now my conductor protrudes out, and what's going to end up happening is, because I've removed the glass, I've moved the barrel wall edge inboard here to this point. So now that z-axis expansion, or in other words, I've protruded um, the copper of the layer into what will end up being the copper plating of the barrel wall. And now my z-axis force along this vertical wall, that's where the copper meets the glass right here, is moved back from this plated face right here to this point right here. And now I have more of a cantilevered bending force applied here. It allows the copper of the layer to kind of flex and bend a little bit without being a shearing force applied directly at this interfacial connection right here. Okay, so that's one form of etchback called positive etchback. Negative etchback, on the other hand, so unlike positive etchback, negative etchback will remove some of the copper of the exposed face of the conductive layer. This causes the copper of the plated through-hole barrel plating to extend into the layer to form the interfacial connection of the conductor layer. Again, this is going to give the benefit of allowing a bending rather than a shearing force. However, unlike positive etchback, negative etchback removes the copper using the same copper etchants we use to form our traces, our circuit, our copper geometries, and therefore does not leave near as much resin or other contaminants on that face. Therefore, you don't have near as much smear removal needed and therefore an easier process. Okay, this leads to needing less desmear and cleaning compared to the positive etchback process. And again, what we see here with the negative etchback, rather than affecting the glass and resin right here, we simply use the same chemical etchant after we do our drilling to eat a little bit of the barrel wall, to eat a little bit of the layer right here. So now during the plating process, the electrolysis and the electroplating protrude into the layer rather than removing some of the glass so it appears the other way. So in both cases, that vertical expansion force right here at the barrel wall is now a bending force rather than a shearing force. And again, it'll look something like this. The z-axis force is applied at this corner point right here, but that is contiguous with our electrolysis and then our electroplating right here. So it makes this appear a bending rather than a shearing force, which again causes us to have a better performance of our barrel wall. So if you are in a high reliability design, or you are in an extended operating temperature range, or you are pushing the envelope to going to higher and higher aspect ratios. Now, one thing I didn't mention, the use of the etchback. Uh, One of the areas of concern, as I said, is the z-axis expansion causing that shearing force at that interface. But we also control that shearing force by our aspect ratio. The smaller aspect ratio is. The larger the diameter of the hole with respect to the thickness of the board, the lower the aspect ratio. The lower the aspect ratio, the less actual shearing force there is here, because when we do the mathematics of the force distributions, the lower aspect ratio, there's more area, cross-sectional area, and so less force is concentrated right here at that barrel wall. As I go higher in aspect ratio, needing smaller and smaller diameter features, there's increased amount of z-axis force applied at that interface, and therefore I might now have a shearing moment happening, in which case I need to mitigate that, and etchback is one of the ways we can do that. So depending on what you're trying to do, etchback may be a solution for you if you are experiencing any of these problems or situations. All right, with that, any questions on the last of the manufacturing slides here? Yes, question.
I just had a question about this etch back, like for reliability. I mean, are we talking like the reliability of getting consistent manufacturing, or are we talking like in a high vibration kind of
Right, we're not
high
talking
temperature cycle?
right. We're not talking manufacturing. The fabricators can manufacture it with or without etchback and get high yield, low scrap rate, regardless of whether or not you ask for etchback. This is we're specifically talking high performance reliability. Think military with extremely wide temperature ranges and products that have to work the first time every time. In the deserts and or the Arctic or whatever the case is, or think high vibration, airframes, jet airliners, fighter jets, and so on. So we're talking performance reliability, not manufacturing reliability here.
And this would be on every like barrel, the
Every
every
plated through
layer.
hole. Yep. Every layer that is attached to an inner layer. So, for example, um, typically what we're going to do, and I didn't talk about it in this slide, I talked about it in my military and my RF for those reasons. Oftentimes, what we do is the fabricators ask to do what's called remove non-functional inner layer lands. So you would actually only have this where you make a connection, because if you have the normal donut of ring that would be around your plated through hole barrel, if there's nothing connected to it, the fabricators just want to remove it because it causes other problems. That's a good point. I should actually mention that here. Although it's not necessarily on our boards whether it'll be a problem or not, uh, during that drilling process. So if you remember on Monday when we talked about the drilling process, right? If
Mm-hmm.
you've ever tried to drill, say, through a piece of metal or anything like that, and you hit the edge of the metal, the drill bit tends to kick sideways, right? Or drill through. If you try to drill through anything and you're right at the edge of the thing you're drilling through, the vertical wall, the drill bit tends to kick sideways a little bit rather than trying to cleanly drill down through, right? And so same thing happens here. So if I'm in the situation, and let me go do a quick little drawing right here. So we have what we call misregistration, right? We've talked about that before, that the layer to layer misregistration can happen. Okay? And that's where ideally, if I have a number of holes, and let me get to a slide right here. Let me go with green first, right? Okay. So here's the thickness of my board. And ideally, I want to drill, let's say I have some pad in my board going to be right here. Okay. Okay. Ideally, we want everything perfectly lined up so that my drill bit, and I'll use black for my drill bit right here, right here. This is my drill bit right here, right? So ideally, that drill bit should be able to go right through the dead center of every single one of the pads, right? This is the ideal world that we want to have happen. Okay. And now let's also assume that just like on our design, we'll assume these two holes right here are what were connected to something on an inner layer. But in the real world, what can happen is that, and I'll use the light blue here, what if this layer right here, rather than being perfectly centered, what if when they etched the layer, that this layer was offset, right? And since this would be a core right here, this layer's offset. And then what if this layer is offset the other way too far? Right here. So as I'm drilling through here, this one right here, this is okay because the trace itself will extend over here, or the plane layer, or whatever I'm connecting to. Same thing right here. I have the trace connecting, so I'm okay. But over here, when I get to this one right here, as that drill bit's coming through and it's hitting the edge, that drill bit might actually try to wander here a little bit, right? It's going to kick off sideways rather than trying to continue down. So basically, the fabricators like to remove all of these non-connected, non-functional lands like you've got here and here, for example. So because of that, back to the issue of etchback, the fabricators, you'll basically only get this on the layers where they're connected because the fabricators say, I'd like to remove the non-functional lands. Now, on the other hand, if you tell them you want to keep your non-functional lands, well, then yeah, you'll get etchback on every layer that's exposed. However, here's the other thing that's going to happen, right? Is even if I have that etchback there, that pad goes nowhere. So do I really care if I get the etchback there or not? Do I care if that one breaks or not? Does that make sense what I'm talking about? And Kevin, did that answer your question? I know I went off on a little side tangent there.
Yeah, yeah,
Okay, cool. All right,
yes,
great question. Any other questions,
yeah,
Kevin, or
yeah.
others?
I was actually gonna follow up with
Perfect.
is are we gonna get to like the different types of fill, like conductive fill and epoxy that you could fill in the views?
I don't normally cover that in this fundamentals one. I cover that in my high reliability, my military aerospace one. If you like, though, I can go over that. Remind me after the break, and we can talk about that. Usually, for a fundamentals class where all I'm really worried about is do you understand the basics of design, getting into the conductive fills, the non-conductive fills, the via protection structures. I usually don't cover that in a fundamentals class, but I can if
Okay,
you like.
okay,
If that's something you're interested in.
thank you.
All right. Any other questions out there? All right. Well, in that case, let's take like 12-ish minutes. Be back at like the what was that? Be back at like the 10 minutes after the hour mark for break, and I will have some stuff ready to show you guys over here, and then we'll get going on the rest of the design work too. We'll continue on with our design work.
Yeah, Chris, if you have time, I'd love to hear what you think about the conductive and non-conductive fills, and then how that plays a part in the reliability or
Sure.
of the joint.
Mhm. Okay, is everybody back from break? I know it's a couple of minutes earlier than I said, but is everybody back from break?
Yes, Chris.
Excellent. And Kevin, are you out there?
I'm here.
All right, excellent. So we'll tackle Kevin's question first about looking at the via protection structure, which I don't normally cover in fundamentals. Usually cover that in more advanced classes, but that's okay. So IPC has a standard here called IPC 4761, called the Design Guide for Protection of Printed Via Structures. And in there, we define several classic methods of what we call via protection. The most basic being what are called tented vias, followed with the filled, partially filled, fully filled, conductive versus epoxy based, and so on. So we'll look at those different structures right here. And we have a number of different structures. Now, the very first thing to be concerned with, to answer Kevin's very first question about the reliability of those via barrels, or my personal opinion on that method. Number one, I never use any protection structure that does not fully fill a via barrel. The reason being is if I do a partial fill, or if I have any kind of voids in there, this then becomes a pressure vessel, meaning as I go through the assembly process, any moisture or other contaminants that are trapped inside of this structure here, when heated, turn to steam, turn to pressure, and can explosively decompress that structure. More pronounced in classic tented vias than in the epoxy filled vias, but we'll see that regardless here. Okay. And so again, you can see some of the damage here. So long-term reliability concerns. One of those is single-sided via protection types 1A, 2A, and 3A should not be used with bare copper hole walls. Any attempt to apply a surface finish to the hole wall that is not protected by plug material, resulting in a partial penetration into the wall, will result in bare copper area at the plug material hole, barrel, interface, etc. Additionally, one of the other problems that happens with these via barrel protection structures, if I'm not fully plugging them, is I can actually have, and even with the full plugging them, if it's not a copper plug, if it's an epoxy plug, is I can actually have mechanical damage to the barrel wall here. I can actually get expansion contraction causing cracking of my via barrel. We'll talk about that a little bit more here in a minute. All right. Now, one of the big things when fully encapsulated by plating or inside a multi-layer structure, CT, T sub G, and outgassing, right? So material specification on the selection sheet right here. One of the biggest issues is the CTE, right? For space applications, outgassing, but the material selection we choose, any CTE mismatch between the material that we're going to plug the whole wall with and the material of the board can cause stress fractures, as we just saw in the previous picture, as well as not only to the barrel wall itself, but even if the barrel wall doesn't fracture, you can actually put enough sideways force that you start getting cracking or fracturing of the glass and resin near the barrel wall face here. So we do have to be very careful about the selection of uh, about the material, especially for thermal expansion, right? CT mismatch. Now, the first type of tented via, a type 1, is, or the first type of protected via, type 1, is what we call a tented via. This is where we allow the solder mask material to cover the barrel hole so the material cannot get down in here. Now, type 1A, you cover only one side. Type 1B, you cover both sides. However, there is a problem with this. Again, especially with just solder mask, because solder mask is a very thin and actually somewhat fragile material when it's not supported, right? Where it's just got the hole there and there's no material underneath it. Again, any moisture that gets entrapped here turns to steam. And if I do a type 1B protection right here, tenting on both sides, that steam can explosively, basically blow out the solder mask barrel right here. In which case, now if this via barrel is underneath the component of the body, like an IC or a resistor or something of that nature, it's been known to do what we call the popcorn effect. Parts literally come popping off of the board before they're soldered into place because of this explosive decompression. This is the most classic protection structure called tenting. So me personally, if I'm going to tent a via, I'm only ever going to do a 1A. I'm going to tent one side so that any entrapped moisture contaminants here during the assembly process have a vent path for that pressure to release through. I'm basically putting a pressure relief valve in. All right. Then we have the type 2, tented and covered. So we allow the type 1 via with a secondary covering. So we do both the solder mask covering right here to tent the barrel itself on a second coating. Or you can do a temporary cap that covers the hole right here with one material, and then come back with your solder mask material and cover the entire surface here. So that's a double tent, basically a double tenting here. Again, A and B version, one-sided or both sides. The double-sided here, although you've got two materials, so you've got a little bit more pressure, um, not retention, but um, oh, I forget the word I'm looking for. Basically, resist out there, right? The decompression there. So you've got two materials there, so you've got a little bit more resistance to the pressure differential there. However, it can still break out, and it has happened. So again, with the type 1 or the type 2, I only ever allow one side of the via to be tented. I want to allow a pressure relief valve, if you will, here. Then there's the type 3. This is where we start to use the plug materials. Uh, Usually it's an epoxy or other non-conductive uh, resin system that will harden and cure, similar to the layer resin, rather than just relying on the adhesive of solder mask or other surface material here. And with the type 3 via here, you are partially covering it. You are not doing a full depth penetration. You're only doing a partial depth penetration right here. Again, A and B, one-sided or both-sided. One-sided, okay. Two-sided, even if it will not decompress vertically through the barrel wall here, anytime I have a void like this where I can entrap moisture or other contaminants from the washing and cleaning processes like at the fabricators, if that pressure, I'm not basically saying I'm not completely ignoring that pressure, but what happens is if that pressure cannot decompress vertically through the barrel wall, it will go horizontally. This is where we start seeing those barrel wall cracks. Then we have the type 4 protection, where we have a partial plug of our resin right here, and then some coating, could be solder mask or a other coating material if you choose. So again, you're trying to coat not only the barrel, but now also the surface of the via right here. Same problem here, again, 1 and 2, where I have a type 2, where I've created this pressure vessel right here, and any entrapped moistures, again, looking at damage to my barrel wall. So basically, so far, for all the via protection structure types right here, the type 1A or type 2A, I'd be willing to accept if I have to put a via under, say, a component body. I'm worried about a solder bridge shorting happening. I'd be willing to accept those. Never the B, where I do the double side. And I never accept the partial plugs right here, because if I'm going to go through the trouble of doing a plugged via here, I personally never use the 3 or 4. Instead, I go with the type 5. The type 5 via here now has the plug material, whatever resin we're using, epoxy, acrylic, whatever it is, fully filling the hole so that I no longer have any entrapped pressure environment right here. I have fully purged and filled the hole. Type 5 just filled, and the surface of the via is still exposed. Type 6 right here, fully plugged, covered with solder mask. And then a different type of 6, secondary film. So type 6 with either the traditional dry film solder masks or type 6 with the liquid film solder masks right here. So either way, the type 6 is the type 5 fully plugged with one or more coatings covering the surface of the pad. And then finally, we have type 7. Type 7 is where we have the fill, and this fill can be conductive or non-conductive. I can do full copper, or I can do a simple resin, But the main thing with the Type 7 is rather than a insulative material like a solder mask, I am now instead doing a metallization plating on the two surfaces right here and coming back and doing a planarization if necessary. This type I use quite frequently and in fact is necessary when we're doing stacked microvias. We're already seeing that in our design a little bit where I have the microvia stacked on a buried via with another microvia. So if I need to do that microvia, I need to have this metallized surface right here for the microvia to connect to. So we will plug and fill. Again, can be conductive or non-conductive. And then we will go and do the capping and planarization with a metallization. So my two types I normally use are the Type 1 or the Type 7. Type 1 if I'm worried about a solder bridging under a component body, a Type 7 if I'm doing my stacked microvias right here. All the others run into some various different problems. Now, a couple of things that the IPC 4761 does not cover is for the covered types right here, the types type 1, type 2, uh, and so on. For the type 1 and type 2, there is an option that the fabricators can do, which is called a barrel cut. Often we're doing via protection of this style because we're trying to protect this surface here to prevent solder bridging that might happen if I have to put a via, say, under a component body. So what the fabricators can do, rather than trying to put this coating completely covering the entire hole, is they can instead extend the coating, liquid solder mask, dry film solder mask, whatever the coating is, right to the edge of the barrel, but leave the barrel itself open. We call this a barrel cut, and there are ways to set that up in the design tools as well as have the fabricators define it for us. That is a very valid method. If I do need to coat both sides, I will do a barrel cut so that I do not create this pressure vessel, but I do protect the surface to try and prevent the solder bridging from happening. Additionally, do I ever use the conductive plating material here? In fact, we have actually a picture of it up here at some of the example pictures up here where you can see copper or other particulate embedded in the resin there. Honestly, if you design your vias correctly, like I showed you guys in week 1 or week 2, where we did the via barrel sizing, right, for the current handling, then there's no need for the more expensive plugging material with the conductive material in there. Again, I'm looking solely for protection to have the plugged via. But this is up to you, depending on your design. If you feel you need the conductive fill, feel free to use it. I, in over 30 years, have never used the conductive fill because I've sized my vias correctly according to the current handling I need. And based off of the current handling, it also handles my temperature rise. So I've got all the thermal conductivity I need, etc. Um, okay, so Kevin, does that answer your question about the different via protection styles?
Yes, thank you.
Okay, excellent. Now, a couple of things I want to point out. So I'd mentioned in the slide about for the etch back, that table 310. Now let's say right here, the total dielectric removal, if we're doing the positive or traditional etch back right here, depends on your board classification of what the total allowed removal of material is, including resin, glass, desmear, and after all processes are allowed, what the total maximum allowed removal is right here. So that's in table 310. The other thing I want to point out, which I should point out right now during the manufacturing portion, at the end of the 6012 document also describes the various tests that have to be performed. So if we go all the way down here, right here. So first off, we talk about the sampling size for the C=0 sampling plan. And then we talk about the smaller the number is here, the more boards that have to be tested in a batch of boards to say that the probability that all boards meet the accepted criteria. Okay, so a 0.1 sampling plan versus a 1 versus a 1.5, 2.5, 4, and 6.5. So if my lot size, for example, here is between 91 to 150 boards for a 0.1 sampling size or sample plan, I have to test 125 of my 150 boards. For a 1, I only need to test 19, 19 for 1.5, 11 for 2.5, 9 for 4.0, and only 6 of the boards to get a 6.5. So again, the higher the sampling number, the less boards have to be sampled in order to show that the product is good. Then 6012 also defines what tests need to be performed based off of your classification. So all of the materials, the fabricators are required to provide simply a manufacturer certification, right? So you're expecting 99.99% pure copper in your board. Well, they ordered the material from Isola, so they simply give you the Isola certification where Isola says they did 99.99% pure copper on the core and so on. And then you have all these various different materials here. So marking and traceability. So the visual. So they have laminate imperfections, plating and coating voids, lifted lens, and so on, workmanship, solderability, surface and plated holes, dimensional, sizes, pattern feature accuracy, bow and twist, solder mask coverage, and so on, conductor width, internal and external, uh, conductor spacings, internal and external, conductive surfaces, for the outer surfaces only, etc. Physical. So, anyways, long story short, there's this long table that talks every single one of the different process steps has an associated test that the fabricator must comply with in order to show proof that the board meets the requirements you have set out in your manufacturing drawing. Now, the other side of that is over here in the 2221. In section 12, quality conformance test coupons, or actually quality assurance, the first section, 12-1, conformance test coupons, are IPC 2221 design standard. Now, you as designers do not actually have to design these coupons. They're already designed for you with certain requirements of like the fabricator has to find the smallest land size and the smallest hole size and set those. But effectively what's going on here is there are a number of different test coupons defined, like an AB/R or an A/R, a B/R, a G, a P, an S, a W, an E, and each of those has purposes. So rework simulation, plated hole evaluation, internal annular ring registration. BR can also do plated hole evaluation, internal ring registration. The G is solder mask adhesion, and so on. So these are the new ones. Then there's also these legacy coupons that were out here. But effectively what these are is, number one, we talked about this a little bit on Monday, and I showed you some examples of those in pictures, is in the manufacturing panel, the fabrication panel right here, the fabricator will put as many images of your board. So this might be your board, and this one they've got 8 images, 2 rows of 4 right here. And then around the perimeter of your boards, they will have these various test coupons where they need to be, like opposite corners, along one edge, and so on. And so you can do, legacy coupons, newer coupons, and so on, or a combination thereof, and how they're worked. But effectively what this design guide tells us, or this design standard tells us, and let me get down here to this, is what the different coupons are, and then the shape of them. Wow, don't know how I got that up there. Can't make that go away. That's interesting. But anyways, there's a special coupon here designed with different size holes, some copper features in there, some interlayer copper structures in here, plated, non-plated holes, etc., that they can go use to measure like these misregistrations and so on. And what the interlayer structure looks like of those coupons and so on. And then there's various different constructions of those coupons. There's legacy coupons right here, or this is the BY coupon right here that has different geometries to it. There's coupons that test the traces on the different layers and how well the material adheres to them. There's this crisscross pattern here of holes. There's surface mount pads, so you can look at how well without a plated through hole, how well the copper adheres to the surface, if it's going to peel or not, and so on. They have coupons for testing layer to layer registration, so they can basically look And each one of these traces goes a different layer, different layer, different layer. So I can say, oh, my connection from my starting point here goes, 20 lines through, but after dot 21, it's no longer making a good connection. Okay, it misregistered enough that I don't have a connection, or whatever the case is. They have test coupons for like the solder mask and the legend ink adhesion. So they do this like crisscross checkerboard pattern right here, so they can do tape pulls to see how well the material adheres, looking with or without copper between them, and so on. The patterns, they can look for surface insulation resistance. So this ladder pattern here, and they can measure insulation resistance between point A and point B right here. They've got other adhesion tests right here. They've got your controlled characteristic impedance for both single-ended and differential structures right here, and they can do as many layers worth as they need, et cetera, et cetera. So anyways, so things like that AB coupon right here, what they're going to do is, even though it's a bunch of holes, they're going to cut this coupon out of the panel, cross-section it right through the midpoint of the holes, trying to get as close as they can. And what they're able to do is look at that stack through z-axis and see if any of these barrels are, these the donuts are offset from the barrel, or where the barrel is from the donuts, and so on. So they can look at those various different registrations, etc. So I want to show you that that exists, that those are all well defined for the fabrication process. Then the other one I want to show you here is the J standard 001. In the J standard 001, this is the workmanship standard for assembly, for soldering. And so this is where we're going to get into items such as, and let me go over here. Now let me go to contents right here. Wires and terminals, through hole, surface mounting, cleaning and residue. So cleaning, I did mention I want to talk about cleaning requirements. We're going to talk about a little bit more next week during documentation, but I do want to point out one thing here. So we talked about, because of the fluxes and solders, that the no clean can still leave a residue. They can be conductive even though it's not corrosive. There is a requirement in J standard 001 here called the cleanliness designator, which is going to be a C followed by a dash and then 2 or more digits. With the first digit, always a single digit, being whether you want no cleaning, single-sided cleaning, or double-sided cleaning. Almost all modern boards will always be double-sided cleaning because we're surface mount. Historically, when it was 100% through hole and all the soldering happened from the bottom side, we used to call it the solder side, you'd only need to clean the solder side. There was no flux added to the top. But now I'll do both. And then I can stack one or more testing requirements for the residue. No, I can say I want it cleaned, but I don't require any testing of the cleaning. Just go through the cleaning process. So that would be like right down here with the 2-0. A 2-1, test for rosin residues, test for ionic surface residues, test for surface insulation resistance, test for surface organic contaminants, or any other testings that you want to define. So I could do like a C22, a C223 if I wanted both sides clean, and I want both ionic residue and surface insulation resistance testing. So you can define whatever that is. And then coatings and encapsulants. We just talked about that over here. And we'll talk about the minimum required coating thicknesses, or range of coating thicknesses, based off of the coating type. So again, 2221 is what's going to tell the fabricator or the assembler what they need to comply with. So most of them, the first three, acrylic, epoxy, and urethane, are all 25.4 to 127 microns, so between 1 and 5 mils basically. Silicones are 2 to 8 mils. Paralenes, or paraxylene is another name for parylene. That's between 0.4 mil and 2 mil, so very thin coating here. And then styrene block copolymer. Again, I have never used this, and I've never heard anybody using this, but it's in there. That's between 1 mil and 3 mil. So our greatest variation is in our standards, our acrylics, urethanes, and epoxies right here, and so on. And then uniformity, bubbles and voids, and so on. So the 2221 is what's going to tell the assembler what requirements they have to meet for how to process the material. All right, and so on. So I just wanted to point out some of those specs and standards for you guys, and some of the things we looked at. We already looked at like the copper area here, but I did want to point out the test coupons here in the 6012 for you guys. All right, any questions on that before I move on to Altium and what we're going to be doing with the next part of our assignment here? Cool. No questions on the IPC standards. Excellent. All right. Then for this week's assignment, it says place all remaining circuits and repeated channels into the board or on the board. Now, so far, last week we just started, we were building the various different parts. So we had, we were at this point right here, we brought all the parts in, we had the rooms, we started routing those repeated rooms using the copying room format, started placing parts. We went over that last week. Yes? Kind of, sort of? Went over a bunch of that last week. Okay. So for this week, now we should be starting to move all of our parts into the board. And so I've got a couple of different versions of that where I'm going to start showing you what it will look like when all parts are placed. Over here. I do want to point out one other thing before I forget here. For those that are not fully familiar with Altium yet, that have not used Altium before, Altium has a interesting feature, and I will say honestly that the big three all have the same capability in one form or another. So whether you're using Cadence, Mentor, or Altium, they all have this where you can define a custom view configuration, meaning, right? So if I go over here and I turn on all of my layers here, and I've got this busy workspace with maybe some routing already done, got all of my parts placed in here, et cetera, et cetera. And I decide I don't want all of that turned on. So I'm going to go ahead and turn all of my layers off. And I'll pick the layers I want. Maybe for placement reasons, for placement, right, moving stuff into the board, I only want to see my two copper layers, my top and bottom copper. I don't care about my inner layers. And maybe I want to see my outline, my legend or silkscreen layers right here. Altium calls them overlay layers. So I might turn those two layers on right here. And maybe I also want to see my plane layers maybe. But for now, I'll do it without the plane layers. So I can go down here and I can say at the bottom of the view configuration here, after I've selected my eyeball, so I don't have to go in and constantly manually click the eyeballs on and off for what I do and don't want to have visible, I can come down here and give this a new name called my layers, and I might call this, you know, placement 2, right? Like that. And so now over here under this layer sets button, this LS button next to your layers that are visible right here, and oops, now this is actually a perfect opportunity. So right now, I'm still missing my bottom overlay. It never got properly assigned right there. So I'm going to come scroll up here and see that I still am missing my bottom overlay. I will click that again to enable that. So now that I have a custom layer name, I'll be able to come down here and hit the little save button right here. They're still using a floppy disk icon, but whatever. I'll hit the little save icon right there, and I've updated that. And then what I'll have over here is in this little LS next to the different layer tabs, I can quickly turn those layers on and off without having to manually go through, turn everything on, turn everything off, select the individual layers. I can just come over here and say, oh, I want my routing instead. So I want to see all of my copper layers with nothing else. And I can go over here and say, okay, I'll go back to placement, or I'll go back to placement 2 that I just created, whatever the case is. So just really quick way to go through and create those custom configurations. Really helps cut down the time when you're trying to go through different modes or behaviors. I'm also going to go over here. In this one, I'm going to go and turn my rooms back on. On this one, I had them turned off. So I'll have them turned on right here. Okay, so if you remember from the PDF that we were looking at, from our Edge page over here from last week, we have this main PDF right here that basically said, here's a rough idea of where we should have these parts placed at. Kind of like that, right? And I'll just zoom in on that a little bit. But I also said this is not exclusive or must be exactly this. I said this is conceptually basic. This is what we call in the chip design world a floor plan. This is where I sit there and say, I roughly want these functions in these general areas, but you are still free to move things around as you see fit. So in this particular instance of the design, I actually modified my design behavior a little bit. And part of that is I'm going to go back over here to the view configuration and scroll up to the top here and show you what I did here using my plane layers. Now, somebody out there, refresh my memory. Did I go over how to create the split planes and define the plane voltage layer definitions with you guys last week? Yes, no? Did I do that with you guys last week, going over how to create these?
No, I don't think so.
Okay, perfect. Then let me go back to this version right here. And remember in our picture that I was just showing you over here, I said we roughly want our analog stuff down here because you can see the switches, pressure, thermistor, buttons, motor drivers. I roughly have analog on the bottom half of the board, and I have digital stuff, FPGA and memory, LCD, LEDs, etc., up here on the north half of the board. That's going to be my starting condition. So before I place any of my parts into my board area, I'm actually going to create my two plane definitions, or my plane area definitions right here. So I'm going to make sure that I have my plane layers defined, or not only defined, but enabled and visible right here. Okay, so I'll make sure it gets all of them turned on right there. And all I need to do to create a split plane. Now, other tools are different. Cadence and Mentor take this a little differently. Altium makes it so all you have to do is drive an area. So as soon as I created that layer in my stack up and defined as a plane, it automatically created a plane area definition, the entire area of the board size. That's a given. That's by default. Altium created that for me. Now, if I want to create an area, however, all I have to do is create a closed boundary. So in this case, I'm just simply going to go to draw a line. And the first thing I'm going to do is I'm going to hit my tab because I want to make this, instead of a 2 mil line, I'm going to make this like a 40 mil line just so that it's nice and big and visible for us. And I'm going to start with a simple rectangle. I'm simply going to make a closed boundary like that. Okay. Now what you'll see is the plane, and I drew that on a plane layer. I now have two different definitions, one here, one here. Okay. I'm going to go ahead and delete that right there. We also have certain manufacturing minimums similar to minimum trace width, minimum copper clearances based off of copper weight, but even beyond copper weight for the layer, for plane layers, the fabricators do tend to like a slightly larger minimum clearance definition compared to what they're willing to do on a signal layer. Most of them like about a 20 mil minimum, but it's a good question to ask your fabricator. What is their preferred minimum clearance on a plane layer? Whatever that clearance is, use that unless you need a larger clearance for voltage reasons. In this case, it could be 20, and I will draw that, but I'm going to draw it specifically with a 21 mil line for reasons that'll make sense later. I want a unique line width, so I'm not inadvertently selecting things I don't want to select when I'm on this plane layer. Now what I'm going to do over here just to create the boundary, I'm just going to start a line right here at my edge. And for now, I am literally going to draw that line right over to here. Okay. I'm then going to come in here and I'm going to select that line. And I'm going to do, I'm going to do a copy of that line. That's going to ask me for a reference point. And I may be going to pick the midpoint of that hole in my what I call my mouse bite. I'll explain mouse bites later when we get to documentation. But I'll put it in that centroid location right there. I'll then go to my next plane layer right here. And I'm going to go Edit, Paste Special. I'm simply going to do the paste on current layer. I don't need an array. And in order to make sure I line it up, I'm going to go back to that centroid. So that's the centroid of that hole. Just makes a convenient alignment point. I'll repeat that on the next two layers. Edit, paste special, paste on current layer. Okay. So now I've created my plane layers. Now, one of the things to talk about right here, and we've talked about this previously, but this is where you can do some planning. In the north half of my board, my digital sections, I actually have 3 voltage rails and 1 return rail. But one of those voltage rails, 2.5 volts, if you look at and interrogate the schematic, you'll notice is only connected to the core of the FPGA. It goes nowhere else. The other two, 3.3 volt and 5 volts, those go all over the place. So I'm going to look at my board that has 10 layers actually. Okay, so this is top, this is L1, plane 1, plane 2, L2, L3, plane 3, plane 4, L4, on the bottom. So that's the way we built the structure of our board. So I have 2 plane layers on the top half of, on the z-axis top and 2 on the bottom. So I have a total of 4 plane layers in my board. Now, when we get to signal integrity, which I don't remember if I did signal integrity with you guys last week, or I think I did that with you guys last week. I don't remember. But if we haven't gone over signal integrity yet, when we get to signal integrity, we'll see why this is. 9 layers. This is an older version where I didn't do this, the symmetry on it. If you come back and take my advanced design concepts class, you'll actually see the non-symmetrical in this design is actually okay because that last layer is A, very thin, B, does not have reinforcement, as only used for the laser microVia layers. So we actually can get away with it, but yes, it should be the 10 just to be symmetrical for the purpose of this class. So yeah, this one probably is missing a routing layer. Great question, Kevin. Okay, anyways, within each of the north half of the board and south half of the board, I've got a total of 4 plane layers. Now the question is, what signal do I want on what layer? Well, I'm going to put a return here, and I might make that my D return. And then I might choose my 3.3 volt here, and then I might take a return here, and then maybe my 5 volt here. On my in my analog area, I might do the same thing and make this the A RTN, and maybe my plus 15 volt here, and then a A return here, and my minus 15 volt here. Again, this is just one possible structure. In both cases, what you'll see in signal integrity, that for every power plane, I want a return plane directly adjacent to it, so I form the planar capacitance I need for the high-speed switching, which we'll talk about during signal integrity if we have not already. Same thing over here, even though I'm not as reliant on the planar capacitance, having it there for high-frequency noise is always a good thing. So this is going to be my plan for layer distribution here. So I'm going to start at this one, and I'm going to pick my north half right here. And either with the properties panels or double clicking on it, I'm simply going to come over here, pick the net, and say this is going to be my DRTN. And I could have just directly type DRTN right there. And I'll come down here. I'm actually going to move the board up a little bit so I can see both halves. So the bottom half, if I did the north half, is DRTN. I'll make the bottom half A return right here. Then on the next plane layer, I said the north half here was going to be, in this case, I still have the plus and minus. I don't have the new naming convention. This is an older version of it, so I'll just use this as an example here. And down here, I said this half here was going to be plus 15 volts right here. Then I'm going to go to my third plane layer right here. This was again going to be D return. This was going to be A return. And I'll go to my last plane layer right here. And I'll make this like my plus 5 volts. And this is like my negative 15 volts. So now I have all of my layer definitions defined. And what we're going to see happen here and let me go find the one I'm looking for. Here. We'll use the JTAG one for now. Oh, there's the one I'm looking for. Sorry, I missed it. So I have a voltage sensing connector. And if I put that connector right there like that, you'll notice because I have those layers defined and I have a plated through hole, 3.3 volt directly connected to its plane. So you can see the different colors of the thermal ties right there. D return connected, 5 volt connected here, minus 15 connected here, A returns connected here, plus 15 connected here, and so on. So anytime I have a plated through hole that needs to connect to a layer that's defined on one of these planes, I simply place the plated through hole and the tool will make the connection for me according to the rules we created last week. Okay. So that's how we're going to do our plane definitions. We'll talk more next week when we get into routing about some additional things we can do with these structures right here, these breaks that we created. There's a really cool trick we can do with those, which I will explain shortly. I'll explain next week. But let's get back to looking at our actual design over here. Okay. So now we've created our border that's going to separate our analog parts from our digital parts. So now is where we're going to start worrying about how we're going to place everything into our board. Now that's where after you've gotten your rooms defined for example. Now, in this one, I'll show you guys this next week why I modified instead of a single straight line. I did this kind of zigzaggy pattern around here. And that's because our A to D converter chip that we are using, uh, most A to D converter chips I've used on the market, they will take the time to go to the next larger package size, like 16 pin instead of a 14 pin, so that they can make sure that all of the analog reference pins are on one physical side of the chip and all the digital reference pins are on the other side of the chip. This particular one kind of split it a little differently. They've got analog pins here and digital pins here and here. So it's an oddball screwball way if I'm trying to straddle an analog to digital boundary right here. So I had to move the split plane boundary so that the analog return, and actually I should move this, try to move this over a little bit and then kick a little bit there. But here's 5 volts, here's the chip select, so that's digital. These are all the analog inputs right there coming from our A to D circuit along with those there. There's the digital return there, and these are the programming connections right here, chip select, clock, um, SDI, SDO, and so on. So yeah, this particular device was not physically laid out very well from an A to D point of view. But anyways, at this point, we'll go over this more next week, but this is the point where once you've created that split boundary, this is where you're going to use your rooms and start placing your individual circuits approximately where you think they should go in the board. I personally, since inputs are on the left, I put my input connectors here. So this one's just a voltage monitor. That's the one we just looked at. Digital voltages are on the digital side. Analog voltages are on the analog side. Now this is just a voltage monitoring output connector here. Then I have the pressure transducer connector, the thermistor connector, and so on. Or I think I have pressure and thermistor in the same one on this one. Pressure transducers. Yeah, I've got pressure transducers, potentiometers, and analog returns on this connector here. And then I've got thermistors on their own connector down here. So potentiometer and pressure transducers are on one connector, thermistors are on the other. So I've got my 2 pressure transducer circuits right here. I've got my 2 potentiometer circuits right here, so that they can route to this connector. And then my 4 thermistor circuits are over here, and they can route to this one right here. I then have my various switches and buttons placed. Now, one other thing, and we will talk about this next week of why I did this way, is we will see that although we have the original 12 Schmidt trigger chips that are normally part of the switches and buttons circuits. Number one, we're going to see an error that I intentionally left in the schematic for the week 3 and week 4, and we're going to talk about a way we can change that using some electrical engineering to make our routing a little bit easier. But what we're going to see right here is one of the things I did is after I got everything placed, so I had the room, I originally had my Schmidt trigger and cap for the Schmidt trigger as part of this room. But then I realized that I'm like, well, technically, that is also a device that's straddling the references. The input is referencing the analog return, while the output is referencing the digital return. So I moved all the Schmidt triggers and their capacitors so that they are directly on top of the split boundary right here. So the input pin is over here on the analog side and the output signal is over here on the digital side. Same thing with the motor drivers, right? In my picture, I originally just had the motor drivers down here in a block, but I realized I'm like, same thing. The input side of the motor drivers needs to reference the digital side, so I can find a way to have them straddle using a combination of rotation and parts placement that we talked about in week 2. I used some of those techniques I talked about, and I took the part and I moved it so that I reworked the design of the room so that I could place the middle of the boundary line right here so that it was straddling the boundary line, so that the analog side or high voltage, high current side was down here in the analog section and the low voltage digital was over here in the digital section. I also moved my power supplies. It made no sense for me to put the plus and minus 15-volt regulators up in this area with all the digital circuitry, since they're going to have a common input of 28 volt and chassis. So I brought my 28 volt connector in here. I can just route 28 volt as a pour down into this area along with chassis down in this area. We'll see how I did that later. And then I can have my plus and minus 15 directly generating right in this area rather than having again to cross the boundary. So more on all that next week. But this week's assignment for you guys is to start with where you were at right here after you've created your split plane boundaries. And you can start with just a simple straight line right here, is now using the PDF that I gave you as a starting point reference. Start placing your parts where you think they should go. One other thing, for those that stayed around, that watched how I built the LCD module right here. Okay, so I'm going to grab the display module right here, and this is where one of my extra layers is going to come in handy. And that's this one down here that I'm calling top assembly right here. So I'm going to turn that layer on. That's my mechanical 15 right here. I want to make sure that I don't also have it down here. Yep, it's that one right there. And hopefully I did that right here. You can at least see the DSP1 right here. In my newer ones, you saw how I also put text orientation, basically meaning when you're placing something like a LCD display, right, that's got human readable characters, it might seem from a routing point of view that this makes more sense in this orientation right here, because my pins are at the bottom and I can just route straight down, except the characters of the LCD would be completely upside down. So be sure that you're also taking into account the text orientation and human readability when you're placing that part into your design, even though my routing is going to be a little bit more challenging right here. Additionally, because this is a part on a standoff, we saw the picture of this. If I look at this in 3 dimensions right here, you'll notice there's a standoff, so there's some amount of z-axis height difference right there. So although it doesn't seem like it, I can go ahead and do things like adding everything except a potentiometer. So a potentiometer part right here that's in that module, that we're going to use for controlling like contrast or brightness adjustment. Obviously for human interface, that can't be stuck underneath, so I'm going to stick that outside. But the rest of the parts, I should be able to go here and do something like, maybe grab the resistors or the chip arrays right here. Maybe it'll let me grab the chip array. There we go. All right, we'll grab the cap. Whoop. There we go, just the cap. And I can leave this on the top side and put this right underneath, right where it wants to be, because of that gap. Now, that brings up one last point before we call it a day. I know we're going to be like a minute or two over. Over here in the configuration gear, or preferences gear, in your PCB editor, under this option here called interactive routing, okay, I'm going to say component pushing, change that to ignore. If I have it on push, basically what's going to happen, if I try to move, let me move that part back outside again for a second. See how it's pushing, right? It's not letting 2 parts occupy the same space based off of their courtyard access rooms, right? So if I've got it on component push and I'm trying to put one part underneath the other, it's not going to let me. So in order to disable that pushing when I'm trying to place my parts, configuration gear, PCB editor, interactive routing, and component push set to ignore. The ignore option right here is what will let you go in and place one part directly on top of another. You do have to be more careful and more diligent about making sure that if you're going to do something like this, that it is okay, because I have the standoffs there. So I know my LCD module itself, defined by this yellow border, is actually some height off the surface, and therefore it will be okay for this part to exist here. And I'll be able to see that when I go back into 3D mode right here. And see my little capacitor right there, sitting happily on the surface of the board with plenty of clearance to the underside of the LCD module right here. Okay. So again, that was the last thing I want to show you guys. With that, again, your assignment this week is just work on trying to place the parts where you think they will be best placed within the board boundary. Next week, we will look at some additional placement techniques, methodologies I use, incorporating these rubber band connections and so on, to see how we would do a little bit more of that placement. All right. With that, I will open it up. If there's any last questions, please ask. Otherwise, have a great work week and happy weekend, and I will see everybody on Monday.
Thanks, Chris. I just had one comment. I resent my email for the Altium Nexus IPC server access. I sent it like 5 or 10 minutes ago, and this time I included the other educational email as well. Education 2, I think it's called.
Okay.
Just to let you know, because I don't think I've received anything back from Altium.
So, well, my understanding is you already have an Altium license at work that you're using, right? You just
I
need
have,
access to.
yeah, just the access to the IPC
Okay.
folders.
Why don't you hang out for a minute, let everybody else sign off, and we'll just fix it right now. We'll just take a look
Cool.
at it. I'm sorry. So
Yeah, sounds good.
let me go grab that right here. Oh, that's interesting. But yeah, everybody else, I will see everybody else next week. Vibe, just hang out for a minute and we will get this squared away for you.
Cheers, Chris.
All right, cheers. I'll tell you what, why don't we do it this way? Let me just pause.